Hello and welcome to another session of Mathematics with Mr. Thompson. Today we're looking again at some things in networks, and in particular we're looking at something called Hamiltonian paths and circuits. So previously we looked at Euler paths, and the thing about Euler paths was we had to be sure we visited every single edge, every line in the network. With Hamiltonian paths, we're interested in looking at the nodes, making sure we visit every single node on the network. And a classic example of this would be something called the travelling salesman problem. And it's a bit like someone has to visit every single destination on their journey once and only once. Or maybe a delivery driver dropping things off on their route. So this is a classic one we're looking at here. This has only recently been minimised, which we'll hear about in a second, visiting all the major centres in every state in the landlocked USA. That's an example of a travelling salesman problem. So to make it a bit simpler, let's look at a very simple one. A Hamiltonian path is a path which visits each node once and only once, and we don't have to end up back where we started. So for this one, I could go from A to B. That would be my first step. Then I'd come down from B and go to D. That'd be my second leg of my journey. Down to C for my third, and then finally up to E for my fourth step. So my route would be A, B, D, C, E, and that would be an example of a Hamiltonian path. Note, it is not the only one I could do. There's a few ways of doing that one, but you get the idea. You're visiting every node once and only once, and you're not necessarily returning to the start. When you do have to return to the start, however, that is known as a Hamiltonian circuit. So we specify the starting point as A, and we have to make sure we get back there. Well, let's just fire in and see what we get. We're supposed to go from A to B, that's 1. That's our first journey. From B, I'm going to go down to F. That's the second leg. Let's make E the third leg. And you can see here that I can't go this way because I'll be blocked. I couldn't go back there, so I can't go that way. I'm going to have to go down to C for the fourth part of my journey, then along to D, and finally back up to the start at A. So our route is A, B, F, E, C, D. And then back to A again. Again, not all edges are used, you'll notice, but it does return to the start, and it does look at every node on the way. Just to finish off, often we're asked to minimise the distance. So in this example, what these numbers represent is it might be the distance between nodes, it might be the time taken to travel, or it might be the cost of travelling that journey. So in which case we'll have to find a route, a Hamiltonian path or circuit, which keeps these numbers to a minimum. And this takes a bit of trial and error. You have to kind of work your way through it and see what you get. So with this one, I'm starting A again. So from A, I'm going to have to, so if I go down this way, I'm going to end coming back up that way, right? So let's go to B first. So A to B. Now, from B I can go either to D or A. So I'll set up a second D or E. I'll set up a second route, A, B to D and A, B to E. Okay, so I've got two journeys kind of going parallel here. If I go A, B, D, the only route I can take is E, C, A. And on the alternative route, if I go A, B, E, the only thing I can do is D, C, A. So that's the only two possible Hamiltonian circuits I can have. Let's put some numbers in. A to B is 9, B to D is 7, D to E is 6, E to C is 10, and C to A is 10, for a total of 9, 7, 6, 10, 10, 42 minutes, hours, days, dollars, whatever. Another one is A to B is 9, B to E is 11, E to D is 6, D to C is 8, and C up to A is 10, for a total of 44. So the shortest path I can take is that one. So Hamiltonian circuits, then we use them to visit nodes, not edges. We can have a path, but we can finish at a different place from where we started. A circuit is back where we started from, having visited every node once, and sometimes we have to choose a path, because there will be often multiple options for us to choose a path which gives us the lowest value.